In part 3, we saw that if we used a transformed variable to create a confidence interval, that at the end we wanted to do what we called back transform that interval so that we could interpret it in terms of the original units that our data was measured in. And what we ended talking about was this idea that this new interval was going to talk about population medians instead of population means. And if we were doing a two independent samples problem, it was actually going to tell us about the ratio of our two population medians rather than the difference. So if we look at our interval from the rainfall example, we had the interval 1.272 up to 7.742. And that interval is a ratio for population median 1 divided by population median 2, where median 1 is the rainfall from the seeded clouds, and median 2 is the population median rainfall from the unseeded clouds. And one thing that's worth pointing out is that whenever you run something in SAS and you have two groups, SAS is going to put those in alphabetical order. So because seeded comes before unseeded, SAS makes seeded our group 1 and unseeded our group 2. The first thing we want to check whenever we make one of these intervals for a two independent samples problem, and then we back transform it at the end, is we want to see if the number 1 is inside of our confidence interval. And that's because of this thing that we saw before, where if our ratio is above 1, that means we think median 1 is bigger. If our ratio is below 1, that means we think median 2 is bigger. And so if 1 is not in our interval, we're going to feel confident that one or the other of our medians is bigger than the other. And we can see that in this interval, we do not have the number 1 inside this range. This whole range is above 1. And so this actually tells me that I'm confident my two groups have different population median rainfalls. And if someone asked me, well, which method do you recommend for increasing rainfall? I would look and I would say, since this whole range is above 1, that means I think population median 1 is bigger. That population median corresponds to my seeded clouds. So I can be confident that the population median rainfall is higher for seeded clouds than it is for unseeded clouds, which means I would recommend using the cloud seeding method if I wanted to increase rainfall. Now, obviously, in real life, other considerations might come into play, like how expensive is each method. We heard back at the beginning that the seeded method involved flying a plane into the sky and actually injecting clouds with something. And so we might also want to know, okay, it seems that the seeded cloud increases rainfall, but how much does it increase rainfall? Because if it's just a small amount, maybe it's not worth it for us to do this. So we need to actually interpret this interval similar to how we've interpreted intervals in the past. So to do that, we can complete the following sort of statement. We can say that we are 95% confident that the population median rainfall for seeded clouds, that's our group 1, is between, and we're just going to plug in the two endpoints of our interval, 1.272 and 7.742, times as big as the population median rainfall for seeded clouds. And what you'll notice is in the past I would have said something like it's this many inches taller or pounds heavier. When we're talking about these two independent sample problems and our confidence interval is representing a ratio of population medians, our conclusion is going to be what we call a multiplicative conclusion. It's telling us how many times bigger one thing is than the other. And I want to point out that we can actually use this template no matter what the endpoints are. So even if both endpoints are below 1, I can still put group 1 here, group 2 here, and just plug in my two numbers. So for example, if my confidence interval had been from 0.25 to 0.5, I could have said I was 95% confident the population median rainfall for seeded clouds is between 0.25 and 0.5 times as big as the population median rainfall for seeded clouds. And if you say something is 0.5 times as big, it's another way of saying it's half as big. So this sort of structure still works for our conclusions. For our actual conclusion here, saying something is 1.272 times as big, sort of like saying it's about 27% more. So 1 times as big would be equal, 1.27 would be 27% more than that. and 7.742 times as big, that's about 8 times as much rain. So what we can see is there's actually a pretty wide range of things that we think could be true here. We're 95% confident that the seeded clouds are giving us more population median rainfall, but that could go anywhere from about 27% more rain to almost 8 times as much rain. All right, so what should we make of all of this? First off, remember that our conclusions are now talking about multiplicative effects, not additive. So instead of talking about a difference in population means, I'm talking about a ratio of population medians. One thing that I mentioned earlier, log transformations don't always fix our problem. So sometimes we might have a data set where either our normality assumption or our equal variance assumption is not satisfied. The log transformation isn't magic. It's not always going to make it so that suddenly our assumptions are okay. In this case it worked, and in a lot of cases it does work, but it won't necessarily work every time. We also saw that if we're doing a log transformation for a two independent samples problem, we're going to check our interval to see if the number 1 is inside of it. That's different from before when we checked to see if we had like only negative numbers or only positive numbers. And again, that's because we're estimating this ratio instead of this difference. And then lastly, I want to point out log transformations can also be used for one sample and paired sample data. They're actually a little bit easier to do in that case because you don't have to worry about this ratio. You just start talking about medians instead of means. A couple other notes about transformations. The natural log is only one possible transformation. We're not going to cover others in this class, but if you took other stats classes or even used statistics in other fields, you might come across a situation where people use like the square root as a transformation, or maybe the log base 10 that we briefly mentioned. We also saw that we're going to perform this transformation when one or more of our assumptions aren't met, but it should be stressed that this can't help us with the random sample assumption. If we don't have a random sample, we're basically out of luck. Some people in much more complicated classes than this one might have some things that you could try to do, but really a lot of statistics relies on us having random samples to work with, because otherwise we don't know if our sample looks like the population, and so it's harder for us to make conclusions about that population. The other thing that I want to mention is if we have our assumptions met, and we run a test or do a confidence interval, but we don't get the results that we were hoping, it would not be appropriate in that case to transform our data and rerun our analysis. This sort of falls under something that's called p-hacking, which is basically a term for trying to find the p-value that you're looking for. And if you do that, your results don't actually have the same meaning that they would otherwise. And so we should really only be using this to try to meet assumptions, not to try and get like one answer or another. All right, so that wraps up the section on the natural log transformation. In Notes 13, we'll start talking about how we might analyze qualitative data and think about trying to estimate population proportions instead of population means.